pressure, I'm talking about really small particles, and they can be liquid or solid, and it's really governed in terms of the EPA by the size of those particles. So in the red here, you can see PM 2.5, that's 2.5 micrometers in diameter and less. In the blue, it's PM 10. So that's things like pollen and dust. And the PM 2.5 is really anthropogenic air pollution related to combustion or anything that creates small particles. And this gray line is a strand of human hair to give you a size reference. And where does this come from? Particulate matter is probably the most ambiguous air pollutant that can be regulated because it can really come from anywhere. So anything that can release a solid or a liquid into the atmosphere is particulate matter. There's natural sources, for example, sea spray, volcanoes, and then anthropogenic sources like automobile combustion, power plant combustion. And then on the lower left, this is a picture of a haboob, so that's dust, and then you can have biomass burning and fires. A lot of the work I do is motivated by the fact that I want to understand what human health impacts are associated with air pollution exposure. And this is just a slide showing kind of the overall process we take to do that. Here's a city with some pollution in it. And then this is a regulatory monitor. So this is part of the EPA network. And we can get a time series of PM concentrations from those monitors. And then we can have a time series of health endpoints. So this can be hospital admissions, emergency department visits, and we put it into this black box, which I don't create that black box model. That would be an environmental epidemiologist developing a statistical approach to try and understand those associations. And then the outcome is the association between the air quality or the ambient air quality and exposure and the health endpoint. So from the whole body of research, including toxicology, epidemiology, we found a lot of information about air pollution health effects. So this is not just my research, this is everybody's research kind of encompassing all of this. And air pollution impacts our respiratory system, which a lot of us would probably expect. If we're ever around a campfire, for example, and the smoke comes our way, maybe we cough or have nasal problems. And then the particles that are really small can go deep into our lungs and end up in our bloodstream. And then it can cause cardiovascular problems. So they've seen things like increased risk of heart attack associated with air pollution exposure. Newer things that we don't really think about potentially as much are the impacts on reproductive health. So low birth weight, preterm births, birth defects, and then also the central nervous system. And this is things like mercury, for example, is a neurotoxin, and they found that a lot of the fish that have the accumulated mercury in them actually comes from the atmospheric transport of mercury emissions from coal burning, for example, that deposits into the ocean, and then the fish eat it, and then we eat that, and it kind of ends up in our blood system, impacting our neurological health as well. So how do we get all of this data to try and understand these health endpoints? On the left, I'm showing what we would call a ground truth. So those yellow marks are where all of the EPA PM 2.5 concentration sensors are. You can see in the eastern part of the country, there's actually quite a few sensors. Once you go into the western part, there's less. And that's just purely because there's less people living there. I was a professor in Nevada right here for about 7 years, and you can see that there's very few sensors in Nevada. They're basically in Las Vegas and in Reno. So we try to supplement that with other sources of information. One example is satellite aerosol optical depth from NASA satellites is what I'm showing an image here. And what this satellite's doing is it's taking essentially a snapshot in time of the spatial distribution of aerosol concentrations as it's orbiting the Earth. So we can try and leverage that information to gap fill where we don't have monitors. Another tool we use is chemical transport modeling. Here's another example that I took from NASA. This is a global chemical transport model. And what you can see here is that this model is really giving you all the physics of the atmosphere, so where all the aerosols are moving to, but also all of the chemistry. So they've color coded these. Oh, also I'm using the word aerosol and PM 2.5 throughout this talk interchangeably. I should mention that. So they've color-coded these aerosols to show where they're coming from. So the white over North America here is sulfate associated potentially with coal combustion. The blue is sea salt, the green is biomass burning, and this orangish color is dust. So this also can give us information where we don't have air quality monitors. What goes into that chemical transport model is a lot of different types of atmospheric models. So the first thing we need to know is all of the physics, and we use a numerical weather prediction model for that. My group uses the WRF model, and this model is essentially using inputs such as terrain and land use information, and we can use observations to try and calibrate the model. And it's trying to solve the Navier-Stokes equations. They're heavily parameterized to give you all of the wind speed information throughout your domain. And the outputs of this model gives us a simulation of all the physical processes occurring in the atmosphere. So anything that you would think would be associated with meteorology. So wind, precipitation, and then also the impacts that the sun has. So the radiation balance at the Earth's surface and things like that. And if we want to understand air quality, we need to know how much air pollution is going into our domain. For that, we rely heavily on the National Emissions Inventory. This is maintained by the EPA. Every 3 years, the states report an annual average by county of the expected air pollution from different sources in their states. And then we use this smoke model to allocate all of that information on grid cells in our domain and getting hourly profiles of the air pollution from the annual average. This gives us the hourly speciated emission rates for every grid cell in our domain. Then we use both the meteorology and the emissions in our chemical transport model. I use the CMAQ model. This is maintained by the EPA. It's updated about every 3 years. This model is a really great tool because it models all of the physical processes that are happening that would impact air pollution in the atmosphere and all of the chemistry. So this would be, for example, your gas phase emissions turning into particles because of the photochemistry in the atmosphere. This gives us concentrations, transport processes, and secondary pollutant formation everywhere in our domain. So that's kind of all of the background information I'm going to talk about today. And now I'm going to talk about applying these tools to the two different cases. The first is going to be temperature inversions. Here's kind of just an overarching motivation for that. The PM 2.5 concentrations, for example, in Salt Lake City can frequently be above the National Ambient Air Quality Standard during the winter time. And those are associated with something that we call a cold air pool. And a cold air pool is essentially a temperature inversion. And by temperature inversion, I mean that the temperature is actually increasing with height in the atmosphere, and it's typically decreasing, so it's inverted. And the Western US is really susceptible to this because of the mountains. So when we have a high pressure system moving in with the mountains, it actually causes sinking air that then changes the thermodynamic profile of that air to create this situation where the air is actually warming as we go up in height. So that makes it so cold, dense air settles on the valley floor. And then these situations are really difficult to model because there's uncertainties in the emissions, particularly with NOx and with ammonia. And the meteorology itself is very difficult to simulate. The chemistry is difficult to simulate, and there's a lot of unknowns. So there's also a limited amount of data for us to be able to understand this process. This was actually highlighted in Science a couple of years ago. I took this picture from the cover of that story. This is actually one picture. This is Salt Lake City downtown, and it's underneath that layer of pollution. And this is the Wasatch Mountains where you can see clearly above it. The results I'm going to talk about today for this comes from the Salt Lake Valley. Here's the Wasatch Mountains here, and this is Salt Lake City. The airport's about right here, and the Great Salt Lake's over here on the left. And this is the Ochre Mountains. So those mountains create this bowl, essentially, where then this cold, dense air just fills up between those mountains and settles on the valley floor. With some research I did a few years ago, we looked at the different types of cold air pools that can exist. I took these two pictures when I was skiing one winter. This cold air pool has a cloud layer on top, and this one is what we would call a dry cold air pool. There's no cloud layer, so this is essentially just a combination of moisture and air pollution in the haze down here. I won't discuss the differences between those today, but it is interesting that they can actually be different. I got really interested in this because I initially looked at trying to compare CMAQ results with observations. This figure here is showing 1 month in February of 24-hour PM concentrations. The dashed lines in the bottom here are all the CMAQ results, and the solid lines are the corresponding monitor observation. And this CMAQ run was not specifically run for this case. This is a national level CMAQ run that people use to look at health effects and in a lot of epidemiology studies. So I wanted to know how good it was in this region. Well, what I found was that during these cold air pool events, CMAQ does not simulate the same increase that occurs in real life associated with those temperature inversions and that air pooling on the valley floor. So I went back and looked at the literature, and what they've found is that the mesoscale meteorology, so the slow moving high pressure system that creates these events, that's really well simulated in our atmospheric models. But you get a lot of simulation errors near the surface, and that's related to the turbulence and the land atmosphere parameterizations that couples what's happening at the ground with the atmosphere above. There's also been a lot of recent papers coming out about the chemistry. There was a field campaign actually also in about 2018 or 2019 in the Salt Lake Valley, where they're really trying to understand the chemistry that happens during these events. So what they find is that the particulate matter is secondary, and the vertical PM concentrations are really critical to the secondary nitrate formation. And the next day, particulate matter is elevated due to the nitrate formation from aloft and it mixing down. So it's a really interesting process that a few people are looking into these days. So for me personally, I did my PhD in atmospheric turbulence. So I really wanted to look at processes related to mixing during these events. And what happens is we get stable atmospheric boundary layers, which also has a decrease in the boundary layer height. So we're decreasing our mixing volume, and we have a stable boundary layer. And all of that is leading to this increase in pollutant concentrations. I have 3 pictures here. This cap here, this is from 2004, so the picture quality is not very good. But you can sort of see blue sky here. This is that dry cap event. Here you can see across the valley. So this is what we would call a mix out period. And here, this is a cloudy cap event. And so you can see that the left and the right look a little bit different. So then when I became a faculty member in Nevada, I had one of my PhD students focus on this for her dissertation. And it was really cool because she could use data from this persistent cold air pool study. So this was an NSF funded study. I actually was not a part of this study, but some of my colleagues at University of Utah led this study. And for 2.5 months, they instrumented that whole Salt Lake Valley with meteorology sensors. Both the surface, they put sensors up the side of the mountains, and they had profilers, both balloons and lasers, to try and get information about the vertical profile of the atmosphere. And so they were able to get lots of good cold air pool temperature inversion events to collect data from. Here's looking at a time series of the PM 2.5 concentrations in the box plot. From that, this is 24-hour PM 2.5 concentrations. And this H22 red line is a quantitative indicator of how stable the atmosphere is. So when that value is increasing, it's more stable. And essentially what you see is during this time period, when we have a stable atmosphere, we have more or higher PM 2.5 concentrations. So during this field campaign, there were 10 really intensive observation periods. I've highlighted those all in blue and red on this slide. The red IOPs were really strong, persistent, multi-day cold air pools. You can see that the strongest one was right here at the beginning of January. So that led to multiple days of air pollution above the air quality standard. And then the blue is weaker cold air pool events. And so my student did the numerical weather prediction modeling for IOP3, which was a weak event, and then this really strong IOP to try and compare weak and strong cold air pools. And then she did air quality modeling for the entire month of January, which covers these 2 really strong cold air pools and then some weaker cold air pools at the end here. So this was essentially her whole PhD, and she looked at trying to understand how well WRF could simulate these events and how well CMAQ could simulate these events. And so she has 2 papers looking at quantifying turbulent fluxes and then evaluating the WRF model performance. I'm not going to talk about those results today, Today, I'm going to focus on her CMAQ results. So looking at the ability of a chemical transport model to simulate this bad air pollution and understanding how the meteorological uncertainties are propagated through the chemical transport model. So she used the WRF model to do this, and her finest domain covered the Salt Lake Valley. It was centered on the Salt Lake Valley. You can see the Great Salt Lake up here on the left. And this is a terrain map. And so you can see the elevation of the Wasatch Mountains on the right and the Oquirrh Mountains on the left. And she used two-way nesting. This was driven with NAM. She also had the observational nudging to try and improve the model performance. And then what she did was had common physics schemes for the radiation and cloud impacts, essentially. And then we were really interested in understanding how well the model could simulate the suppressed turbulent mixing. And so she did some sensitivity testing of all the schemes inside WRF that impact the turbulence simulation. And this ended up being 4 different model configurations using ACM2, YSU, MYJ, and the MYNN boundary layer schemes. So what this really is, the planetary boundary layer is simulating how much mixing you get vertically. And then the land surface model is simulating all the land conditions. So how much the ground heat flux goes into the atmosphere, and then also the absorption of the sun's solar radiation. And then this surface layer model is the model that couples those together. So this can be thought of as coupling the land and the atmosphere. So all 3 of these models here calculate different aspects of this configuration. So I'll just summarize what she found when she did all this sensitivity testing. And essentially, WRF does pretty well for weak cold air pools. So the WRF model's been getting better and better over the years. 10 years ago, it didn't simulate the temperature inversions very well at all, but now it does okay for weak ones. But when she simulated that really strong IOP5 case, the WRF model started to kind of break down. And when she dug into it deeper, she found out that the surface exchange coefficient in WRF is overestimated, and that leads to an overestimated insensible heat flux. So essentially the WRF model tries to put in too much surface heating, and that leads to too much mixing in the model. And there needs to be updates to the Mononobekoff similarity theory, which is used for the turbulence closure in the WRF model. So now I'm going to talk about her CMAQ results. So she used the same WRF configurations to drive CMAQ, and then we got the 2011 National Emissions Inventory data from Kirk Baker at the EPA, and this is the CMAQ details for the chemistry that she used. So first, we looked at the valley heat deficit, this H22. So this is what is giving us the indicator of how stable the atmosphere is. The black dots are the observations, and all of the different lines on here indicate a different CMAQ model simulation. The CMAQ model results are all comparable, meaning they're getting very similar answers, but you can see that during these cold air pool events, this is that IOP5 at the beginning of January, the strongest temperature inversion they had. Right at the beginning of this, the observations show a really stable atmosphere. That H22 value is getting really high, whereas the CMAQ model does not see the same stability. It does better toward the end of that cold air pool event, but then you can also see that in the second cap and the third cap, it's not getting the stable atmosphere as strong as the observations are seeing. So then if we look at the simulated PM 2.5 concentrations, this is now hourly concentrations. Again, observations are in black. So during that first cold air pool event, we see in the observations that there's just this continuous build of concentrations. There's a little bit of breakup in here. There was some high winds that came through, but really it's building throughout the whole event. And this matches what other researchers have seen. It basically increases 10 micrograms per cubic meter per day throughout the event, and it builds in PCAP2 and builds also in PCAP3. And the CMAQ model sees here that there should be elevated concentrations during this event toward the end compared to when there's no cold air pool, but it puts this diurnal profile on the PM concentrations that we don't see in the observations. So we looked at why this could be. So the valley heat deficit, this slide I just showed before, You can see, especially at the beginning of this event, where the stability of the atmosphere is not captured in CMAQ. The model doesn't know at the beginning that this is going to build, basically because it's not getting the meteorological processes simulated correctly. We also wanted to know how the emissions were impacting this. So we looked at the NOx concentrations. So we have ambient NOx observations from the EPA monitors. And we can see that the underestimate of the PM is not driven by underestimates in NOx, because the NOx concentrations from the CMAQ model are actually sometimes higher than what we're seeing in the observations. So we didn't think the emissions were what was leading to this underestimate that we were seeing in PM 2.5. Another way to look at that is to stratify our results by cold air pool times and non-cold air pool times. So if emissions were the only thing driving this discrepancy, we would expect that the non-cold air pool and the cold air pool to look the same. But what we see is in this non-cold air pool time on the right-hand side, if we look at this quantile plot, the observations are on the x-axis and the models on the y. We can see that for most of the simulations, we're falling on a 1-to-1 line for the PM 2.5. Whereas for the PCAP times, we're really underestimating the observed PM 2.5 concentration shown on the left. So this also illustrates that meteorology is likely a problem in simulating these events. And then if we look at the chemical composition, this is non-PCAPs again on the right and PCAPs on the left. What we can see in terms of just looking at the observations, for example, the first bar is observations, the PM 2.5 is much lower in the non-PCAPs cases. So we're reaching probably about 13 micrograms per cubic meter here, whereas during the PCAPs, we're reaching about 42 micrograms per cubic meter. So that's a big difference. The other thing that changes is when we have a non-PCAPs, we have nitrate and organic carbon dominating, whereas during the PCAPs, this is the majority of the PM is ammonium nitrate. So then if we look at the different simulations, the 4 CMAQ runs are on the right in both of these plots. We can see for non-PCAPs, we're actually overestimating a bit the PM concentration, but the distribution of the species is very similar to what we see in the observations. Whereas during the PCAPs, CMAQ is really underestimating the ammonium nitrate formation. It's still saying that the PM is largely driven by organic carbon and nitrate. So this is just a quick summary of all the air quality modeling that Xia Sun did. So she found that in the CMAQ model, the PM 2.5 is really underestimated during those PCAP events. We do not think that this is driven only by the emissions. The NOx seems to be a little bit overestimated. We don't have ammonia observations to compare to. There is a chance that that is actually underestimated in the emissions, but for sure the meteorology is not adequately capturing that stable boundary layer that happens during the caps, which is leading to some underestimated PM 2.5. And then it seems that the ammonium nitrate is also being underestimated, so that could point to some uncertainties in the chemistry inside the CMAQ model. So that's all I'm going to talk about for the temperature inversions today. So I will move on to briefly discussing some wildfire smoke related research that my group has been doing. And this research really started when I was living in Reno, because Reno is downwind of California, and so we are really heavily impacted by wildfire smoke in that region. This is showing some time-lapse photography looking south into Reno from the mountains. And this is one afternoon. You can see on the right there, all that smoke just gets pushed into the valley. So this was during the Yosemite Rim Fire in 2013. And you can see that all the smoke, again, because it's in that valley and the mountains kind of block it, just stays pooled in there throughout the evening. The motivation behind this is that the smoke is harmful to humans. You can see that in August of 2013, this is hourly PM 2.5 concentrations. The EPA standard is this green, and we're, for the latter half of August, always above the standard. And that was, again, associated with the Yosemite Rim Fire. The picture on the right is looking at the aerosol extinction essentially for the sun. This was my PhD student. She focused her whole, another one focused her whole dissertation on looking at trying to use satellites to model the smoke. So this is 4 o'clock in the afternoon, and she's taking her camera, pointing it directly at the sun and taking a photo. So that's virtually impossible to do because the sun is so bright, but there's so much smoke in the atmosphere that it is extincting enough light from the sun that she is able to take a photo of it. So not only is there health impacts from wildfire smoke, there's also radiative forcing impacts associated with climate from this smoke. And then because there's more drought in the Western US, we're seeing larger and larger and more wildfires. This is showing an example. This is from a colleague of mine, Matt Strickland, looking at the health impacts of smoke. So they had some preliminary data from Colorado. And what I'm showing here is that the PM 2.5 concentration, as it increases as you go to the right, the odds ratio, so the likelihood of going to the emergency department for asthma increases. So this is what we would expect. And really, we want to be able to understand how much of the wildfire smoke is contributing to this versus the anthropogenic air pollution. So to do this, we try to use satellite images, or the satellite aerosol optical depth. This is looking at visible images for 3 years, and there's major fires every year in California. And this is showing Reno is a star in each of these. This middle one is the Rim Fire, which I've been showing data from. And you can see that the fire originated in the bottom part of this picture, and this wind is blowing all the smoke up toward Reno. So then when the satellites try to quantify the aerosol optical depth, we have issues because there's the aerosol layer vertically in the atmosphere is not uniformly mixed, and not all the aerosols are confined within the boundary layer, meaning that the aerosols can be injected really high up in the atmosphere with these fires that happen in the Western US. And then also the surface reflectance we've found really impacts the quality of the AOD retrievals from satellite. So this is a really basic, simplified schematic of satellite remote sensing for aerosols. So what you have is you have a satellite sensor that's orbiting the Earth, and it is actually relying on the sun as the energy source to be able to quantify the aerosols in the atmosphere. And so you can see that this total spectral reflectance here is the sum of the reflectance from the atmosphere and also the Earth's surface. So then you use a radiation transfer model to take the amount of radiation you would expect from the sun that the satellite is sensing to back out the concentration of aerosols. So it's a really heavily modeled situation when you're getting the AOD values from satellites. So you can imagine that you have to back out what's coming from the surface. So your surface albedo, so the amount of radiation that's able to reflect from the surface, impacts the quality of the retrieval. Also, you have to assume what types of aerosols are in that aerosol layer in the radiative transfer model. So if you have lots of different types of aerosols mixing together, that can create some uncertainties. And then it's impossible to detect the aerosol layer when you have clouds. And so there's cloud screening algorithms built into these where it will remove the information if there is a cloud present. So there has to be a way to detect the clouds. So this is showing just a map of, so if you look in the middle, it's California and Nevada. And this area in the northern part of the state where there's a really bright desert, that's the Black Rock Desert. That's where Burning Man's held every year in August. And so when my student came to me and showed me the AOD concentrations or the AOD values for the month of July, I said, why is it so polluted in the Black Rock Desert? Literally nobody lives in the Black Rock Desert, and Burning Man isn't until August. So this is too soon for there to be aerosols in the atmosphere from that. And so we realized actually that the places where there's these high values of AOD, where we would not necessarily expect them, they seem to be spatially correlated with the high values of albedo, meaning it's where there's bright surfaces on the Earth. And then we found out that that is impacting the radiative transfer model in the AOD retrieval algorithm. So there's these artificially high AOD values showing up in the Western US. So I've done a lot of work related to wildfires. So the whole interdisciplinary goal is to understand the effect of smoke on emergency department visits in Colorado and Nevada. My former postdoc, Sasonica Ivy, did a lot of air quality modeling for this. I'm not showing those results today. Today, I'm going to just look at the satellite retrievals. So my former PhD student, Marcela Loria Salazar, focused her dissertation on this, and I have a new PhD student now that has also been going down this. So our objectives for this work has been to try and develop a model to analytically quantify AOD remote sensing uncertainties, and to use that model to look at the physical properties that are impacting the quality of AOD retrievals that we get. So this is similar schematic to what I showed before, but now it's looking at the simplified radiative transfer model that Jingting Huang developed. Here's the sun. So the solar radiance from the sun comes in, goes through our aerosol layer, and then there's the reflection back to the satellite, and then also the reflection from the surface, and then through the aerosol layer again. So essentially what's happening is all of these reflections get modeled in this radiative transfer model. And this is really simplified. So we're not accounting for lots of scattering back and forth from the aerosol layer to the surface, surface to the aerosol layer back. We're looking at just one radiation comes in from the sun and then is reflected from the aerosol layer and the surface. We're looking at one reflection. And when she did this, then she got an analytical model for the radiative transfer model. And then we used a propagation of error approach to look at the different physical processes impacting AOD uncertainty. So she looked at surface albedo, the single scattering albedo, and the asymmetry parameter. And then also, as you take the limit of all these derivatives as they go to infinity, this is a critical value. So this would be values where you're not able to actually get the AOD information from the radiative transfer model. And here's just a quick plot showing using that equation of the critical value. So this is a strongly absorbing aerosol. So this would be urban aerosols as an example, and surface albedos on the x-axis, and then the AOD error is on the y-axis. So as you get close to this critical value, the AOD errors go to infinity. So basically, if you have that value of surface albedo, you cannot detect the AOD value using a satellite. On the right is the same plot, but for desert aerosols. So these are a weakly absorbing aerosol. And so it would be reflecting light, and then the surface albedo. The value here of surface albedo 0.36, that's similar to the values we see in the Black Rock Desert. So what this is showing essentially is that we can't detect bright aerosols over bright surfaces. And then over here on the left, this 0.186 value is what we would see kind of over urban areas. So you can't detect strongly absorbing aerosols over a strongly absorbing surface. So this is intuitively what we would expect, but this is just showing that her model shows the same thing. The really interesting thing about this is that the Black Rock Desert, so this is the albedo value from a satellite over all of the Black Rock Desert, and the histogram shows that we're getting a value around 0.4 or around that critical value where then we're not able to get AOD. So now it makes sense that we're getting those really high AOD values over the desert because the retrieval algorithm has a hard time because of that bright surface. The other interesting thing that we found, though, is that the albedo values from satellite, so the figure on the right shows these red lines, that's from MODIS satellite, don't match what we're seeing if we go out and quantify the albedo on our own. So it's really underestimating the albedo values. So if the radiative transfer model from the satellite is using the satellite AOD values, there's already a very large uncertainty going into the radiative transfer model or the satellite retrieval algorithm, leading to high uncertainties in the AOD from satellites. Another thing with the satellites is we get data removed because of cloud screening. So wildfires create a lot of moisture, which can then condense as the plume is transported up in the atmosphere. So the satellite record removes a lot of this information thinking it's a cloud. So you can see, for example, one day of the rim fire, the middle image here is showing that there's a lot of missing AOD from the satellite because it's getting cloud screened. And so my PhD student is working on using data analytics and machine learning to try and improve the gap, the missing data and gap filling the AOD record. So this is just an example of that on the right. In summary, it's difficult to use satellites in the Western US to quantify AOD. A lot of that's because the land surface types change a lot. There's heterogeneous aerosol mixtures, and the surface reflectance from the desert regions create a problem. And so we're trying to come up with ways to improve the satellite AOD algorithms and gap filling approaches for that. I didn't show the air quality modeling results, but because of these satellite issues, that's a lot of times how we try and estimate wildfire emissions. And so the problems with the satellite AOD also show up in our wildfire emissions inventory, where if there's clouds over the fire, the satellite doesn't know there is a fire. So if we rely on that to model them with CMAQ, then we're missing information. So wildfires are actually a really difficult thing to study. And so I feel like I'm going to be in business for years with my research group focusing on these, but those are some of the limitations and challenges. That's all I have for today, and this work is not my own. This is largely the work of my former PhD students, Dr. Xia Sun and Dr. Gloria Salazar on the left, and my current PhD student, Jingting Huang on the right. And this is where I've been getting financial support for this work. And with that, I'll take questions.
All right, I'd like to thank Dr. Holmes for her talk, and I'm assuming y'all can hear me. And if you have questions, please ask as many questions as you can. We have about, we have a little over 10 minutes, so plenty of time for questions.
Yeah, I have a question. I was wondering, I feel like I've heard of satellites being used for like gas pollution concentrations. Like, correct me if I'm wrong, but I'm just curious if you're familiar with like how different the mechanisms for measuring those are, and like what kind of like uncertainties you might run into with those opposed to like aerosols.
Yeah, so there is, so OMI is doing ozone and NOx, or some, I think it might be NO actually. So there are satellites that are doing, and there's actually a satellite for CO concentrations as well. So I personally don't work with those right now, so I can't comment on the uncertainties they see, but all of the satellites rely on a radiative transfer model to assume anything. So for example, also with the aerosol retrievals, they have to assume the gases in the atmosphere as well. So to retrieve AOD, we're assuming how much ozone is in the atmosphere to try and back out the aerosol contribution. So my impression is that because they all rely on a radiative transfer model and lots of assumptions about what's existing in the atmosphere, there are likely uncertainties depending on where you're at in the world and things like that.
Cool, thank you so much.
Yeah. So there's a question in the chat from Andres. How will data collected during the pandemic be managed in the models since many operations were not business as usual? So that's a really good question. So all of the CMAQ model results I've shown, they're not calibrated to observations. And so it relies heavily on this emissions modeling. And so the interesting thing about the pandemic is that in the cases where things were really shut down, it potentially provides a unique test case for us to evaluate the models, meaning that the ambient concentrations we see are almost like ambient with the removal of a lot of anthropogenic sources. And so we can run test cases with the model, varying the anthropogenic emissions in our model to get it to match the observations. And so that's kind of one way that the pandemic has been unique in being able to provide these test cases. But for sure, the models I use the smoke model to allocate all of the emissions, those right now don't account for the pandemic situation where everything was shut down. Like I would have to go in and manually change all the behavior patterns in my emissions modeling to be able to simulate the shutdown.
Heather, I have a question.
Yeah.
So if you go to your slide where you show, I think like you had like 4 or 5 different CMAQ runs, or maybe they were WRF runs. And I think you had mentioned that all 4 models track each other really well.
They're similar, yeah.
They're very similar, yeah. I'm just wondering if these different model runs used, different sub-processes and parameterizations, why are they so similar?
Yeah, so this is actually a good question, and this paper's in review right now, and we're getting a similar question. So the thing that we varied in these different CMAQ models was the turbulence parameterizations in WRF. And so the interesting thing is that if you look at only the WRF scenario and comparing the WRF configurations and the results you get there, you see differences. And so we see less of a difference in the simulated air pollution concentrations, which is interesting, but also not interesting. So the interesting thing is that you would expect the turbulence model differences to propagate through the PM modeling differences. And we are hypothesizing that a large reason we don't see those differences is because to be able to use WRF with CMAQ, you have to run like a pre-process or a post-processor for WRF, pre-processor for CMAQ. And in there, they recalculate a lot of the vertical mixing, like the vertical eddy diffusivity, using one PBL scheme. So basically what it means is that it doesn't matter what your WRF is getting. I mean, it matters in terms of the temperature and the wind speed and things like this, but all of the turbulence variables are going to get recalculated by one PBL configuration before you run CMAQ.
Okay.
It's kind of a vague answer to your question, but none of the chemistry, we didn't run sensitivity on the chemistry. So all of them are running the same chemical mechanisms.
Okay, great. Thank you.
Yeah.
So another question would be, during the wildfire events, are you also, I don't know if you've looked at ozone, are you seeing a big increase in ozone as well?
Yeah, so actually, Sunny, Dr. Ivy is working on a paper right now. We have a really unique data set in Nevada. One of my colleagues got funding from the state of Nevada to set up an ozone network. So like I showed that basically Nevada has no air quality monitors, and Nevada is exceeding the ozone standard or about to exceed the ozone standard. And so they wanted to be able to basically blame California for the ozone problem. And so they gave her a bunch of money to go out and monitor ozone throughout the state. And so then we have all of these, we have 2 years, so 2 summers of California wildfire simulations that overlap with when she had this extended ozone network. So we can look at urban versus rural and look at the fires. And so the interesting thing with fires is that immediately downwind of the fire, ozone is depleted. But then if you look about 1 day transport downwind, all of the ozone concentrations go up from the fire. So yes, we're seeing increased ozone concentrations from these fires as well.
Is the decrease immediately downwind of the fire, is that due to the fact that you have less photochemistry because essentially the plume is limiting the amount of radiation that reaches the surface?
It's more related to the NOx and the VOC concentrations. So it's similar to how when you look in like downtown urban environment, you have less ozone, but if you look as it's being transported downwind, there's more, and that's because of the NOx and the VOC concentrations.
Thanks.
Yeah.
So we have time for another one or two brief questions.
Oh, hi, Heather. This is Mingming Lu. So, we might have met a few years back. So,
yeah, we did.
Yeah, we have quite a few students in my air pollution class, and we are talking about inversion, and we just covered the PM 2.0 criteria air pollutants. So sounds like Salt Lake City has some air quality problems.
Yes.
So
yes.
can you, winter and summer might be a little different.
Yes.
So can you comment on the air pollution in Salt Lake City, the major pollutants in different seasons?
Yeah, absolutely. So Salt Lake's really interesting because it doesn't run high on an annual average. And so then for Salt Lake, you have to look at the daily concentrations essentially to see these air pollution events. So in the winter, the air pollution problem is largely related to 24-hour average PM 2.5. And so essentially when an inversion sets in, the PM concentrations, it takes maybe 1 or 2 days at the beginning of the temperature inversion for it to get above 35 micrograms per cubic meter. But then it will stay there for about 5 days until there's like a major wind event or a storm that comes through. So if it snows, it will knock out all of the particulate matter. But then once a temperature inversion comes in again, it will all be elevated. But they also have a summertime ozone problem there as well. So in Salt Lake City, they have it's very much a commuter area. There's about, I think, 3 to 3.5 million people living between Ogden and Provo. And so that's about, I don't know, maybe an hour and 15 minutes driving. And a lot of people commute. So there's a lot of automobile pollution, but then there's also a lot of refineries, right? Within 5 miles of downtown Salt Lake, there's, I think, 4 refineries about. And so there's a lot of emissions that then form ozone. And then also in the summer, what's really interesting is the stagnant conditions that lead to the temperature inversion. So the high pressure subsidence, that also creates problems in the summer because you get stagnant conditions when you have the high pressure system. So you can get a buildup of the ozone pollution in the summer. And then if you look at the Uinta Basin, so just east of Salt Lake City toward Colorado, there's not a high population out there, but there's natural gas extraction happening and oil extraction. And so they're having a wintertime ozone problem, which is very unique. And so the snow on the ground also really kind of enhances the photochemistry because the sunlight is being reflected off the snow and causing high wintertime ozone problems.
Oh, wow. That's good to know. Thank you.
Yeah. It's called the Uinta Basin.
Here's another question in the chat. Maybe you can give a quick answer.
Yeah, I like this question. Okay, so Orem is down by Provo. And so my favorite ski resort is actually Snowbird, but Snowbird can be very busy. And so on the weekends or on holidays, there's a lot of people there. So for skiing, I go to Alta a lot, but they don't allow snowboarders. So if you snowboard, that one's not a good one. But Solitude and Brighton, the next canyon, Big Cottonwood Canyon, they get a lot less people. And so if you're looking to get away from people, those are very good choices. And then hiking trail. There's so many good trails. I don't even know. There's actually really good trails down by Draper, which would be between Orem and Salt Lake. So if you didn't want to drive super far away. And then also the Provo Canyon, it's not really like a hiking trail, but they have a little paved path. I used to road ride up there quite a bit, and that's really pretty. So there's lots of good things to see near Orem. Oh yeah, Bell's Canyon. Cool.
Well, I think we are out of time. So let's thank Dr. Hong for a very interesting talk. A lot of really cool